All right, it's time for our last talk before lunch. A request for all of you guys, we record these talks and put them online eventually. I don't know that we have the last ones from last year online yet, but they will get up there sometime. So if you could, please wait for us to bring the microphone so that we can record the questions in addition to the answers. It makes a big difference for people who didn't get to attend. Second thing, if you're a speaker or a trainer and you haven't seen Kat yet, we have something for you, so please visit her at the front. And now we have Dmitry and Thomas, who were kind enough to step in and give their presentation on research in security issues in hardware cryptocurrency wallets.
Thanks. Yeah, so we were talking with George yesterday, and we saw there's not a whole lot of hardware talk, so we're here to fix that because we'll talk about hardware wallets. So yeah, this is our presentation from CC, by the way, so maybe one or two of you have seen it, but hopefully you'll still learn something new if you haven't seen it. So I'm Dmitry. Some of you know me because I've talked at REcon a couple times. This is Thomas. And also our buddy, our friend, and our colleague Josh isn't here this time around. So yeah, but with the three of us, we actually started doing cryptocurrency consulting. So for everyone in this room, if you're looking for an industry that needs security people, because there's currently no security people working in that industry, it's cryptocurrency. You can talk, if you buy us drinks, we'll tell you lots of stories about New York hedge funds and whatnot and how terrible their security is. So we have a bunch of people to thank, so we'll just get it kind of out of the way early. So know that we appreciate your contributions. So we started this actually last year, right around the time of, right around REcon, we started discussing that we should take a look at these hardware wallets because every one of us does hardware. So I mean, we also teach classes around hardware, and so these look like a nice target, a nice embedded system to look at. So we started a Telegram channel. It was 50,000 messages at the time when we did talk in December, but since then I think it's even more. And I even had my first son in the meantime, so it was like a long period of our life. But in general, the motivation was we looked at these hardware wallets, and I've never had research where we had 100% of the things that we came up with to try, 100% of them worked. So that's just to prepare you. Okay, so what we wanted to do, so this is like the list of things that we wanted to check out. So we wanted to look at the supply chain. We wanted to make sure that we wanted to show some of the hardware vulnerabilities that are there. We also wanted to demonstrate and find a side channel attack, because that's pretty typical for hardware. And also the chips that they use are actually not very secure. So we were pretty sure there'd be a chip level vulnerability as well. So I'll just briefly discuss what a wallet is, just very quickly, because some people don't know what the mechanisms are. So essentially, it's just an asymmetric key pair. So asymmetric cryptography. You have a public key and a private key. Then essentially you use the public key to receive Bitcoin or cryptocurrency. You use the private key to essentially prove that you're the owner and create new transactions and send the cryptocurrency. So from a hardware point of view, or what you need to keep secret, you actually only need to keep the private key secret, and the public key part you could in theory publish, and that's essentially your address. So, but basically that means that for every cryptocurrency, you need to store one key pair for every cryptocurrency that you have, et cetera, and every address. And so that's a pain in the butt. So people came up with something better, which is a standard BIP32, BIP44. And essentially that means that you create one seed, cryptographic seed, so essentially one source, and then you derive a bunch of wallets from it. So you can derive, like essentially you create one, and then you have an address for Litecoin, Bitcoin, Ethereum, and you can have multiple addresses for each one. And as a side note, that's also what exchanges do when everyone gets addresses. They're deriving for wallets on the exchange, they're deriving a unique address for you, but this is all ends up being, goes into their wallet. So essentially, so you basically have like an offset, you add some crypto, it's all based on ECC, and then you can generate new private keys and new public keys, et cetera. So long story short, if you do it this way, the cool thing is you only have to store the cryptographic seed. but it's a pain in the butt to write down. So what do people do? You basically do a mapping of the binary data of the cryptographic seed to words from the English dictionary. So there's a standard dictionary of, I can't remember, I think it's 4,000 words. And so you're mapping the bytes of the key to words. And if you've ever set up a Bitcoin wallet and you had to write down the words, that's what you're writing down. So it's basically making it human readable and easy for you to write down. So that's kind of the initial thing. So let's talk about hardware wallet really quickly. So people at this conference have heard about malware before. It's a thing. So instead of storing it on your computer that could get owned, you store it on a hardware device, which sounds like a brilliant idea. So basically, you send the transaction to the device, and the device actually signs the transaction for you instead of the cryptographic seed being on your PC. So the seed is on the wallet, and the wallet is actually doing all the cryptography, or at least the final cryptography that you need. So you can actually see the transaction and confirm or deny it with a button press on the hardware wallet. So that's essentially what they do. So it internally signs everything and sends it back over USB. For the most part, USB. There's some Bluetooth wallets as well, but essentially that's the idea. And then, but one thing that people always forget is this has to get broadcast. So there's always a computer there, and that's also potentially an attack vector depending on how they implemented it. Is you need to actually send it to the network for it to get registered, for everyone to know about it, and for it to get integrated in the next block. Okay, so that's the introduction to what a hardware wallet is, which Colin skipped yesterday. So here's supply chain attacks, which is a real vector. Especially, I don't have to explain, hopefully, to people in this room that red teaming is like a thing, or it should be a thing. You would hope for hedge funds and whatnot. But yeah, so the manufacturers are pretty conscious about their supply chain. So they use stickers, which is infallible, of course. They use different types of stickers with holograms, with unique serials. So here's our buddy Joe Fitz made these. So they're Fitz 140 approved stickers. One of the funniest things was when we were preparing this talk, we were actually looking. So also you can, just to show you that the stickers are not great, you can still open them up and close them, and we'll see the tool of the trade for performing this attack in a second, but it's totally doable, and you won't be able to see this. You're normally not sitting there carefully studying the holographic sticker for fingerprints and DNA residue. So the counterfeiting is actually a problem, and it was funny, when we were preparing this talk, there was actually a blog post by Trezor, and they were explaining that they've been finding Chinese clones that are using the sticker, but the Chinese clones, ironically, were using the old style of sticker. So they successfully made a copy of the sticker, but it was the old style of the sticker, which meant that, so basically they had a blog post saying, if you buy a wallet right now, then the sticker looks like this, but it's not, it's a valid sticker, but it's the old sticker. So if you had a wallet, for example, in an Amazon warehouse somewhere with the old sticker, it would also have this. It might also look like this. So anyway, stickers are terrible. We don't know whether the wallet that we were taking a look at was actually a fake or not. So that just shows you how that doesn't really contribute to security if you can't even tell if it's the correct sticker or not. And how do you remove stickers? So this is Josh just before our CCC talk, hours before the talk, using a fancy Dyson hairdryer to remove the stickers. This works pretty well. It doesn't leave a lot of residue, and you can see with the tweezers it comes right off. So kudos to Josh for that one. So then the Trezor T, which is the newer model of the Trezor, they thought about this longer. So they put the sticker on the USB port. Because clearly you can't remove it. So Josh overcooked this one a little bit, but you can remove it without it actually leaving residue if you pick the right temperature. So another manufacturer, Ledger, they actually go so far as to say, did you notice we're so secure, we don't need a sticker, is what they say. So it's in the box. So then the next question you might ask yourself is, all right, you got me there. The box doesn't have a sticker on it, but how difficult is it to open the device? And turns out the Ledger's actually by far the easiest one to open. So we all have different techniques. I prefer the toothpick. Some people use fingernails. It's really up to you. But you can really open all of these, even though some of them are ultrasonically welded. Ironically, I would say from the clones that I've seen, if the seal is not good on the Trezors, that's actually also a good way to identify a counterfeit, because the original ones actually do a decent job of ultrasonically shutting it. But if you can open the enclosure, you might be asking yourself, what can you do? Well, you can reball the device, essentially what George was just talking about. So you can replace the chip, load a chip with your firmware. So it's a real problem. Basically, you remanufacture these devices, close it, the user doesn't see, and now they're using. You can get to the point where they're using a backdoored device as well. So one more thing that we looked at was actually was to create an implant would be another attack vector. So so we wanted to build an RF implant for this thing. So this is also, Josh helped us out. And everyone remembers the Bloomberg story last year, the Bloomberg Business Week story with the big hack. So we wanted to riff on that one as well. So now we have a small hack. We're gonna attack the ledger. So we also went overboard on domain names. So Josh registered supermicro.fun for this one. But the goals of the hardware implant is that you can basically, you have the device in there, it fits inside, the user doesn't see it, and it bypasses the security function. So this is Josh's part, and Josh has a ham, so he's allowed to do 433 megahertz. But what we were doing is essentially building an implant that could press a button. So why would you want to do that? And the reason is that if you now have, if you own the PC, you can send a transaction, and then you would be able to, over RF, confirm it remotely. And by remotely, I mean from tens of meters away. So we made this PCB, which we have hundreds of. If anyone wants them, come talk to us, so that you can go and backdoor all of your friends' wallets. But it's basically, it's as compact as we could make it, yet be super easy to solder with your hands. Like if you wanted to go even smaller, it'd be totally possible. We just want to make sure that hand assembly works well. So you just have to, the only pieces that are missing are a couple components, a transistor and antenna. So the antenna will be coming up, but you can see here it is on the left. It's on the ledger. On the right, it's on the Trezor, so you can see easily fits in the cases. And you can even play with it in a breadboard because it has standard spacing. So then, antenna design. Tried a couple things: straight antenna, squiggly antenna, spiral antenna. We ended up going with a squiggly antenna. And as everyone knows from the hardware world, if it fits, it ships. So that we went with that one. So then, ironically, I remember we were sitting in the chat, and Josh was very worried because it wasn't working for him. He connected the ledger and was surprised because he was connecting it, and they do a check if the device is genuine or not, and it wasn't working. But then it turned out that it was just Josh's Ubuntu. So then when he tried it on Windows, everything was fine. I mean, there's like, for a moment, Josh nearly had a heart attack thinking there was some way that the device could detect it, but obviously couldn't. So here's nice pictures of Josh's chair that he used for testing in his basement. And he ran out of basement was the problem. So this thing could go even further. So at 50 watts, he was easily getting 11 meters with his transmitter. So here's a little video of that part. So what do? You plug the device in, and essentially what's on the screen is it's showing you the transaction that you can either confirm or not. So I'll start it, and so you'll see in a second. It's showing you the address, the transaction amount. So in this case, it's actually sending test currency, but there's the RF radio, so think of it like a walkie-talkie, and so you'll see confirmed transaction, he hits the button, and then the transaction gets confirmed. No physical press of the button necessary. So anyway, so the backdooring these devices or intercepting them and putting an implant in is a real threat, even though the manufacturers kind of discredit this one. So again, you wouldn't be able to do this one with just the device, but you would essentially have to own the machine that they're using, but then you could confirm transactions. So hopefully this one will end up on Mr. Robot in the next season. Also at one point we were discussing all this stuff and studying one of the wallets. There was a very funny hex constant, and Josh said if you use funny hex constants in your code, people won't be laughing with you; they'll be laughing at you. And Josh said this. Josh said it would end up on DEF CON slides, so it's not DEF CON, and it's no longer CCC; it's REcon. So we had to update that one. But yeah, so now Thomas is going to talk about that.
Yes, so as said, we wanted to look at supply chain attacks, but we also wanted to find firmware vulnerabilities. And so one of the devices we looked at was the Ledger Nano S, and we found a vulnerability that we call Food Babe. And we did not come up with this name. This is actually literally in the firmware, so don't blame us for the name. So let's briefly talk about the Ledger Nano S. It's a very simple hardware wallet. It has like 2 buttons, a USB port, OLED, and that's basically it. And if you take it apart, you will see there's really nothing to it. It's a small PCB, a small screen, that's it. And the Ledger Nano S has actually a secure element, so an ST31. And then also an unsecure chip, which is an STM32. And if you turn the PCB around, there's actually 5 pins that look a lot like the STM32 programming port. And turns out this port is enabled, as shown by other people before. And Ledger says this is not a problem. So let's look at the Ledger Nano S security model. So the idea is that you have these 2 chips with the buttons, the display, and the USB connected to the STM32, which is just a microcontroller, and then the ST31 being on its own. And so they consider the left side unsecure and the right side secure. So basically, the left side acts as a proxy, and the right side runs the app, stores the seed, and does all the important stuff, basically. And so if you, this is better. If you put in a transaction, the transaction request will go from the computer through USB to the STM32, which will then forward it to the ST31. And the ST31 will then say, hey, please display this transaction details via the STM32 on the display. And then the STM32 will check the buttons, and if you press yes, it will go to the ST31, and the ST31 will sign the transaction, send it back via the STM32, via USB to the computer, where it then gets broadcasted to the internet. But the problem is, if you pawn this unsecured chip, you can sign your own transactions. Like you just tell the secure element, hey, yeah, we totally displayed this to the user, and he said, yes, don't worry about it, just sign it, give it back to me, and I'll take care of it. But hardware attacks with a debug port are kind of like physical access and so on. And so we started looking at the firmware upgrade process. And so the firmware upgrade is verified using some cryptographic measure, and we cannot simply send a custom firmware to the device anymore. It used to be possible, but now it's not. And assuming it's done right, this can be kind of hard and time-consuming to reverse engineer, and also can lead nowhere. And also the bootloader used to be open source, but now it's completely closed, so we really have to reverse engineer it from scratch and so on. But so after a lot of time in IDA Pro, we basically found that the bootloader accepts different commands. So one of them is select segment, where you basically say, okay, I want to put in a bootloader upgrade, and it will start at this address. Then we can send some data to an offset of the target address. Then we can flush it, so basically just make sure it's written to flash. And then finally, we need to call sequence_boot, which is basically a function that verifies the flashed code, and if successful, it puts this constant, foodbabe, to a certain address. And only if this constant is there, the device will actually boot. So basically, when you start the device, it will boot, it waits 500 milliseconds. If a button is pressed, it goes to the bootloader. If not, it checks the address 0x800 3000, and if it's foodbabe, it boots the firmware. So our first attempt was, hey, we just write this ourselves. So we select the address where the constant needs to be, we load foodbabe in, we flush, we reset. Doesn't work, damn it. But so then we looked at the verification they use to prevent you from overwriting it. And so basically what they do is they do a whitelist of if your destination address is in this range, you cannot write to it. And if the destination address is specifically the address of foodbabe, we will just write zeros to it. And then we write it. But it turns out if you read the datasheet of the STM32 very carefully, by default, the flash is also mapped to a second address. And if we look at the code again, it only blacklists a certain address where you are not allowed to write, and it doesn't whitelist where you are actually allowed to write. And so what we can do is simply we replace the address we write to with this mirrored flash. We load, we write foodbabe, we flush, we reset, and we can flush custom firmware. And so what do you do when you're a millennial and you can run code on a device? You run video games. So in this case, we ported Snake to the Ledger Nano S, and it takes like 2 seconds to install. Ledger says this is not a problem, because they are protecting against this kind of attack. And how do they do this? They do something they say checks the STM32 for authenticity. So basically on boot, the STM32 sends its firmware to the CQ element, and the CQ element verifies the firmware and also measures the time it takes to send the firmware, with the theory being, well, you can't decompress it so fast to send a fake firmware in real time. Well, turns out we can. We boot a compromised and compressed firmware, we copy the extractor to RAM, we jump to this extractor, and then really extract the data back to flash. And then we can just use the original code to send over the entire firmware, and the ST31 will happily verify the firmware and happily boot. And the problem is that all the big compressions are kind of hard to do, but if you just find duplicate bytes in the firmware, you basically get enough space, like 250 bytes, to write a compressor, a decompressor, and even some malicious code. We wrote a proof of concept of this that is not offensive and will be released soon. And also this whole bug is documented by Live Overflow. So we worked with him to describe how this works and byte by byte walk you through the exploit and how to do this at home, basically. We had also some public releases for analyzing the CQ element protocol and so on. So feel free to check it out on our GitHub. Ledger also has a more higher end device, which is called the Ledger Blue, and it has this nice shiny color display and so on. And we call this section Fantastic Signals and How to Find Them. And so this bug took 5 minutes roughly to find. Yes. So basically when you open the device, you see there's like a touch screen, there's a CQ element, there's an unsecure processor, just as before basically. But if you notice, there's a particularly long trace between the CQ element and the main processor. And so does anyone know what is a long conductor with a fast changing current? It's an antenna. And so we pulled out an SDR and basically just look at, with a very shitty antenna, look at the radio spectrum of the device. And when we do this, we can basically see, as soon as we enter a digit of the pin on the display, we see a bit of a radio signal coming out, but it's very weak. But don't worry, because luckily an antenna is included with the device. They call it a USB cable, I don't know why. So if we connect the USB cable to the device and do the same, you can see that actually you get like this giant spike, which you can receive across from 10 meters and so on. And if we start analyzing the signal, we can see that it's like these single bursts, then a pause, and then bursts again. And so we used the logic analyzer to find exactly the signal. And it turned out to be the display test points, the display bus, basically. And if we look at the signal, for example, blue is the digit 1, orange is the digit 2, we can see after some filtering they're very, very different. And so we can actually differentiate from the signal the different digits of the pin. But writing DSP code is kind of boring, and we also absolutely needed to have more buzzwords in this talk. And so we decided to hack blockchain IoT with artificial intelligence in the cloud. And the idea was we record training signals, we pre-filter them, we train an AI on it, and then we profit. But training an AI requires you to press the button like a million times just to get a decent, a decent training set, right? This needs automation. And so one roll of duct tape and Arduino, a cheap servo later, we had this wonderful enterprise device, which spends hours doing this. So we have our data recorded, and then to do this scientifically, at the beginning we split it into two parts. We have our training set and then our validation set to validate this actually works. So we do pre-processing, TensorFlow, AI model, basically just read a book on TensorFlow and you will know how to do this. And we did the test set, pre-processing, and wanted to see how well does our AI perform. And so TensorFlow can split out these wonderful graphs which show you how accurate it is. So basically it tells you the accuracy, how likely it is to be a certain digit, and also the visualized signal. And turns out that we get 90% accuracy of stealing the pin remotely. And you can actually get this publicly, so we ran this on the Google Cloud because they have free GPUs. And so hit me up if you want to take a look and play around with it. We have a version released with only 5 digits in the training set to not be fully offensive, but yeah. And with that, I'm giving back to Dmitry.
Yeah. So the next thing that we wanted to look for was an actual chip level vulnerability in one of these wallets. So this one affected the Trezor one, was the wallet that we were looking at specifically. So just briefly on the Trezor one, just like the Ledger, it's a very similar idea. So 2 buttons, USB, and an OLED display. But with this one, there's only 1 chip, so there's no extra secure element, and there's no, like, conceptually from the architecture, there isn't a secure, basically a secure, dedicated secure area executing, secure code, let's call it. But the cool thing was, so when we started working with Josh actually did a talk at DEF CON a couple years ago where he exhausted lots of avenues of trying to actually do a glitching attack. And the best part was that he already designed a breakout board for us to work with. So this is essentially, so Trezor is open source, so you can go download from their GitHub, you can get the design files, you can get the code as well, and you can build your own Trezor. So that's exactly what this is. It just breaks out all the signals that we need and just makes it easier to play around with. So you can see right here, he initially used the chip whisperer without success. Colin. But eventually, I mean, we could have, we'll see that it'll work as well. But at the very least, he verified with the chip whisperer that this chip is pretty susceptible to glitching. I mean, he could get it to corrupt certain data values and whatnot. And he kind of exhausted it, but unfortunately, we couldn't, with this work alone, we couldn't turn it into something that we could exploit. So then we started working together, so the 3 of us, and this is what we did next. So turns out there's actually quite a bit of research since the STM32 is such a popular chip. There's quite a bit of research on this, and I think there's even one paper which might be published by now. If not, I mean, will ask me later. But essentially, there's a couple of people that have already looked into this, and the gist, and so if you look at the STM32, the ST Micro product portfolio, basically all the chips at the bottom have already fallen, have been slayed, and then there's still some chips that people haven't looked into. But for the ones at the bottom, there's already public research on attacks that you can do against them, and there's a lot of reuse, especially in this class or category of microcontroller. So we would expect those attacks to, at least a certain variation of those attacks, to carry over to some of the other models as well. But specifically, the one we're interested in for the Trezor is the STM32F2. And so how does it work? It has something called readout protection. So essentially, you set this, so you lock the chip down, and what that means is, so ideally you would set it to RDP2. That means you have no access to any of the debugging signals. The bootloader is disabled. Game over. You cannot do anything. That's what STM says. But then, but when you get the device, it actually ships with RDP0, which is fully unlocked. You have debug access. You can flash the device, etc. And so this is just a state in which a manufacturer could actually put code inside of it and go from there. So what we wanted to do, if you look at the patterns, the pattern for unlocking the device is AA. The pattern for locking the device is CC, and that's the state that the Trezor is in. So it's not likely that we'll be able to flip all the bits and get into AA, but if we get anything other than AA or CC, then you actually end up in a state that's called RDP1, which gives you access to RAM, and you can read and write the RAM. And so I think my explanation is like why, because I think some people in the room might be asking themselves, who would need this as a mechanism? Why would you want this? And I assume it's so they can go in the field and essentially collect crash dumps from the device or see where a device got stuck, connect the JTAG and get an image of RAM. But when you do this, you can't do single stepping, you can't access flash, so that's all protected. So you can only get a snapshot of whatever's in RAM. So basically, just with an arrow, we want to downgrade from RDP2 to RDP1, which is a slightly more lenient version of the RDP setting. So we started off looking at how the device boots, or actually, I mean, we didn't do this, we just exhausted glitching, so we were glitching in 3 different, I mean, we each had one of these setups and we were glitching in 3 different countries simultaneously, and found this one empirically, but to do it correctly, what you actually need to study is how the system boots, and for that, you can do power analysis traces. So using what's called just a measurement across the shunt resistor, you can begin to see how the device boots. So up top is the supply voltage, so you have to power cycle the device, and then you can watch the I/O pin behavior to determine where it's actually booting. So you can see it actually takes 1.8 milliseconds, which is very slow for a microcontroller, for the device to boot. So now you know it takes really long. Let me start taking a closer look. So now, so you can see right there, that's where it boots. So now you can also watch the reset pin, because the power on reset on the STM32, you'll see that the pin floats eventually. So this is this trace, so you can see it right there. So it's actually, after 1.4 seconds, it floats the pin high, which means it's probably starting to actually boot. And at 1.8 seconds, we know it's already executing our user code. So at some point between 1.4 and 1.8 is where the glitch is going to be. So that already reduces like our parameter space by a lot. And so then you continue to study it kind of more and more. So now it's the power consumption trace again, and I'm just looking at I'm basically looking within that 1.4 to 1.8. I'm looking at 200 microseconds, and turns out you can actually see even more detail about how the system boots. So you see where the boot ROM begins to execute. You can see where the option bytes get read. So I just care about the timing offset, right? So I assume that's where the option bytes are, because you can see that the power consumption goes up. So when the curve gets a little bit more crazy, that usually is a sign that more stuff is getting access, hence there's more current, so it's consuming more power. But you can actually even see where it drops to the user code as well. So now you've really reduced it to this 200 microsecond section of where something's actually happening. And if you try to perform this attack at home, then this is where you need to look. So what does it look like? What's the setup? No chip whisper involved. Sorry, Colin. So I use a FPGA board, a multiplexer, and we have the Trezor at the bottom and the debugger. So just running this, you set it up, you run it, you basically lower the voltage and hope magic happens and you flip a value or two. So on the scope, it looks like this, and I recommend if you're doing this in your home office, the key is to turn the scope towards the door. So you can see even the trigger that I'm using is not great, but it's good enough. And you just turn it towards you, and that way, if you get up at night to get a glass of water or because the baby's crying, you can see the scope, and you're like, oh, okay, it's still running. It's not finished yet. But essentially, if you do that, you just use standard JTAG tools, because we're going to re-enable JTAG. However, the JTAG will only be able to read SRAM. So you use OpenOCD. OpenOCD has this wonderful command called, which one is it? Yeah, dump image. I just couldn't remember by heart. But you just need to look for, in the datasheet, for what the memory offset is. And if it works, it works. So in this case, you can see I wrote a file called sram.bin to the desktop. And you can essentially go from there. So Thomas is going to tell us how to get the code into RAM.
Yeah, so the big problem the big problem we had at this point is we can read the RAM, but how do we get the seed from flash to RAM? And so we started reviewing all kinds of code paths and tried to find a way to get the seed from flash to RAM so we can read it. And it turns out that the firmware upgrade procedure doesn't require a pin. So and the firmware upgrade also retains data. And we wondered, how does this work? And so we started reviewing the upgrade procedure. And basically, if you start the upgrade, you will see that there's a function called backup metadata, which copies everything that's on the user storage basically into RAM. And so it's a simple mem copy from a flash pointer into RAM. And so the idea was we go into the bootloader, we start a firmware upgrade, and we stop before the RAM gets cleared. But unfortunately,
yeah, sometimes it gets stuck. So Colin also talked about this. I mean, when he was up here glitching the device with his Bitcoin actually on there. So I would not do that. I've bricked more of these devices, I think, than Colin has. But basically, once you start the install, it's already wiped the flash. So starting at this point, you can actually try to connect over with OpenOCD and dump the memory. So initially I thought that because I thought I was in a hacker movie, I thought I only had enough time until the bar fills and I had to be very fast. So I was sitting there hitting like up arrow and enter on the keyboard or doing it in like a for loop, and it was pretty unreliable. And then I screwed up like one time and I thought the seed was gone forever. But it turns out after you finish the firmware upgrade, it shows you a SHA like 512 or 256 of the firmware that you upgraded, and they do not delete the seed until you hit confirm or deny. So actually, it turns out there's no timing constraints like in this attack. Like if you get it working, then you start the upgrade procedure. It's like 100%. Like if you manage to get it into a state where you can read the SRAM, it's 100% success rate. There's like no way that this will not work. So yeah, so basically, if you see the screen or the previous screen, that means the seed's already in RAM. I recommend waiting for this screen because it's not, it's more reliable, and you don't have to wipe the sweat off your brow as you're watching the progress bar slowly fill up.
Yeah, and so at this point, the seed is still in RAM. We can open OCD, the full RAM, but the problem is then you get like this big hex dump, and so we needed to build a tool to analyze this dump. And so luckily we were able to find a super sophisticated seed extraction tool, which is made for this job basically. And it only runs on certain POSIX compliant systems. It's really complicated to use. It's called strings. And so if you just run strings on the dump, you might see something you've seen earlier, which is a lot of strange words after each other. And this is your seed. You just stole all the bitcoins off the Trezor using strings. And there's no encryption of this. They're just in plain text on the device. And there's also this 1, 2, 3, 4 is actually our pin. And so to make this a bit more efficient, we built this device called the Trezor Glitcher, which you just plug onto an FPGA board and you put in the chip using a hot air gun. You just pull it off, put it in there, and you get the seed. And so yeah, this was patched by Trezor, I think 6 months later or something.
I mean, not 6 months. It was,
three,
it was 60 days.
Ah, sorry, I
Yes.
apologize. Yes. And so after our talk, a lot of these vendors responded, and so we thought we would briefly talk about responsible disclosure, because we got a lot of bad feedback saying we did not do responsible disclosure. So let's talk about FoodBabe. FoodBabe was reported on the 20th of July 2018. So I wake up the next morning and the response from the vendor is, this is obviously not a bug. I mean, you're playing Snake on a device. It's not on a secure device. It's not a bug. So then we gave our talk, and suddenly it's a vulnerability and was fixed 2.5 weeks later. And also it turns out that the same bug was first reported by somebody else a few months later. So this company left a bug for 7 months,
I think it was
or
more
even
like
more.
9 months.
Yeah, open in the public and did not even bother to patch it. And then on their blog post, they actually call us out and say and imply that we don't do responsible disclosure. And so this is not how responsible disclosure programs work and how they should work. And so this industry has a lot to learn somehow. repetition there. Okay.
So yeah, so I mean, where do you go from here? So one thing that we're currently working on is actually looking at the secure element, so the chip that's inside, because the claim was always that you cannot actually, we didn't succeed to extract the seed from the secure element on the ledger because we were able to compromise it without doing anything to the secure element. But that's actually one thing that we're looking into now is with the SEM images of the actual ST31. So next thing, if you guys are interested in this kind of stuff, just as a shameless plug, we're actually doing a talk at Black Hat this year about all this kind of stuff and about glitching and how that what implications that has for chips. And since .fail is such a great TLD with lots of domains yet to be registered, the talk's going to be chip.fail. So check that out at Black Hat, and that'll cover some additional devices and some further improvements to the stuff we talked about here. And if you're interested in, if you're a cryptocurrency company or you deal with cryptocurrency, you're an exchange and whatnot, feel free to get in touch with us. I mean, that's what we do. So you can find us and find some of the details of this talk on Wallet.fail, Wallet.fail on GitHub, Wallet.fail on Twitter. We retweet funny stuff, and you can email us or get in touch with us individually as well. So yeah, thanks.
Thank you. Are there any questions, or is everyone hungry? Awesome, cool.
Cool.
Thank you.